Okay, so let's start looking at that Huygens principle. So if you read Huygens principle, you've learned that basically what Christian Huygens described was that a wave front, this is a wave front, is nothing more than a bunch of little wavelets, all emanating new waves at each point as it moves forward. And the wavelets only transmit the wave forward. So if you imagine infinite amounts of little wavelets in here, then you would end up having them all touching tangent to this wave front line that I'm making right here. And that would form the wave front. And that's where the area of greatest amplitude would be. And so that's how he pictured a wave transmitting through space. And that's what we're going to use as our principle to understand the concept of refraction and how his Snell's law is derived from here. So let's just go ahead and go to imagine that we have this interface down here, and imagine this wave is moving in this direction. It's going to travel into this interface. Maybe this could be, again, as we just used the other day, water, and it's now presently in air. Oop, spelled air wrong there. Let's see if we can erase that. Try again, air. So we have it going from a index of refraction of basically 1 here to maybe 1.4 or so down here. Not to be exact, I'm not going to worry about it too much. I think it's 1.48. There we go. Now I have it exact. Okay, so on this next slide, what we're going to do is we're going to just get rid of the little wavelets to make that a little bit easier, and we're going to imagine this water interface right there, and imagine that we've got wave fronts coming at this water at this angle like this. So this is air again. Having trouble spelling air tonight, and water. And so I'm going to imagine that here's another one, and notice they're equally spaced and approximately so. And so now I'm going to take this one right here and just this one has moved into it a little bit, and then this one has we need to make that refract just a little bit right there. So this is going to bend a little bit towards the normal. There we go. Okay, and so now the next wave would be bent in like this, and we're going to compare that to a wave. We'll just compare it right there. Okay, so I think we've got our setup here for everything to be set up. So think about this. So if I would have made these equally spaced, if we were to take and draw a perpendicular representing like a ray right here, and another perpendicular representing like a ray right here, in a way, then we can see that we have two nice right triangles with a common hypotenuse. And so let's go ahead and label this A, and let's see, D, E, and no, I'm going to erase that. I'm going to try to follow your textbook a little bit for you. So you can go back and read this again later, and E. So we have two angles. We'll call that theta 1, and we'll call this one theta 2. So as you can see, the area highlighted here in yellow has bent towards the normal. And so, but it's hard to draw a normal in this. So that's how come we use the ray model, because it's much easier to draw a normal. And so you can see it, though, that has bent towards the normal if you were to imagine a normal perpendicular to the plane of the water. So let's take this, and I'm going to go ahead and get rid of that yellow there for a minute. Okay, let's think about this. So this wave is traveling at some velocity, v, and down in here is traveling at some velocity that's a little bit less than. So this is v in the air, and this is v in the water. And so, okay, so I'm picking back up from Friday when we were deriving Snell's law. And if you look right here, and you just look at the outline that I have, and I'll just pick a new color for this. I'll pick yellow. So this triangle, and let's pick a pretty blue for this one. This triangle share something in common, and that is a hypotenuse. So that, if you remember from that wave front has bent as it entered into the water, and so it's going slower. So if we just look at this, so think about this. This is the wave front. If you think about it, remember that was the wave front, and here's another one from C to D. And if we talk about that, then we say that the change in time from D to A is the same as the change in time from C to E. So remember that here in just a minute. So let's just define a couple things that we could say. We could talk about the change in time as the velocity of the wave is equal to the change in distance or displacement over the change in time. And so we could talk about that. We could say that the distance that it moved from D to A, so D to A, we could say that distance is equal to the velocity in air times the time. And from C to E, we could say that is the velocity, and I'm just going to put a W in water times the time. So remembering that, let's move forward to the next screen and see what we get. So just a quick drawing. We've got one wave coming in here like this, and like so, and the other wave coming along like that. And just to get our drawing back in perspective, and we'll go back and check, and we had E, C, D, A, E, C, D, A. So we know that this is theta incident, and this is theta refracted. So if we did a quick little bit of trig here, or we'd say that sine theta incident is equal to AD over CA, and sine theta refracted is equal to CE over CA. So if we divide this equation, sine theta incident over by sine theta refracted, we end up canceling CA, and we're left with sine theta incident equals AD over sine theta refracted equals CE. So I'm going to grab that and copy it, go to the next page, and paste it right there. And if we think about that, if you recall, going back 2 screens for you, that dA was the velocity in air times time. So the velocity in air, so we could rewrite that as sine theta incident equals the velocity in air times time over sine theta refracted equals the velocity in water times time. Then we know that the times are equal, so we can cancel those. And then all we have to do is get rid of the v's and get them in some way of index of refraction. And I'll sort of leave this with you to follow this up. So what I'm going to remind you of, though, is that the index of refraction, recall, was the ratio of the wavelength, you could express it in a wavelength, but of the velocity of light, in this case, in this, and we'll use air and say that air is very close to a vacuum, so in air over the velocity in the new medium, but in this case it's going to be over air, so therefore velocity of air would equal velocity of air, sort of sounds weird, over n air, so that will give us the index of refraction of air, and that of water would equal the velocity in air, which we're saying is almost 1, over the velocity in water. And that would give us that the velocity in water equals velocity in air over n water. And I think you see if you substitute these in, like for instance this for here, and this one for here, and then you do a little bit of the velocity of air would cancel out, and you'd be left with Snell's law. So we'll wrap that one up there and close that up. So hope you can follow that.